I guess whatever the topic of my talk is here should fit completely because it describes precisely what we have been doing in the last 6 months here. So this is joint work with Alessandra Iozzi, Anne Parot, and Beatrice Pozzetti. And Alessandra gave a talk in the quasification workshop, and if my talk looks very different, it's because in the last 3 weeks there is a lot which has been going on. Okay, so our object of interest is a compact surface which is going to be, for simplicity, without boundary, even though the whole theory goes over for surfaces with boundary and gets a little more complicated. And the context of my talk is what is called higher Teichmueller theory. And to say somehow where this comes from, so recall that Teichmueller space itself can be seen as a quotient by the PSL2R conjugation action of a set of the set of all representations of the fundamental group of sigma into PSL2R with the property that they are injective and with discrete image. The point here being is that this here is precisely the union of two connected components of the real algebraic set consisting of all homomorphisms into PSL2R. Okay? So this way of looking at Teichmueller space suggests that what about replacing the group PSL2R by other Lie groups and then saying, well, okay, so maybe there are some interesting connected components of this representation variety which, depending on the Lie group, will lead to interesting representations. Okay, so of course that rationale here is after the fact, you know, after people have shown some interesting theorems. You can actually, in this case, say this. So anyway, this is hindsight 2020, right? Okay, so there are two strands here, essentially, even though it's more complicated. One direction is if you replace G by SL R, or more generally, real split groups, and that leads to the theory of the Hitchin component. And the other is, and that's going to be my topic, SP2 and R, or Lie groups of Hermitian type. And this leads to the theory of maximal representations. And okay, so that's what I'm sort of going to talk about. My talk is about maximal representations. I'm not going to define what they are. I'm just going to give examples. So, maximal representations. You can, okay, here's one definition. Which, that's the set of all representations for which the Toledo invariant attains its maximal possible value, which is n times 2g minus 2. So that definition might suggest or not something. What is important here is essentially this is a set of representations which is described using intrinsically the property of sp2 and R, namely that it acts on a Hermitian symmetric space. So there is a Kähler there's a Kähler form, there's an invariant 2 form. And when you have an invariant 2 form, you can sort of create an invariant for surface group representations, because you know the 2 of the 2 form and the 2 of the dimension of the surface sort of are the same 2. Okay, so it's sort of the area of representation which is maximal, and that's one way to look at it. It can be seen as the first Chern class of something. So this here is a union. The important point is it singles out a union of connected components of the full representation variety. And I can give you here are fundamental examples. So, and these examples are sort of constructed in sort of following way. You take something obvious and then you say anything connected to this is of the same kind. So here we're going to take the lift of some holonomy representation of a hyperbolic structure. So put the hyperbolic structure on sigma and then lift the corresponding holonomy representation into SL2R and compose it with a specific linear representation of SL2R, which must have some non-degeneracy condition, namely pi. So pi is a sum of symplectic representations. That means, you know, pi is a direct sum of irreducible representations, and the irreducible components are vector subspaces which should be non-degenerate for the symplectic form we're considering here. So then, this is an example of maximal representation. Can you take what?
Can pi contain the trivial representation?
No, cannot contain the trivial representation, because the trivial representation is one-dimensional, and a symplectic representation is at least should be at least two-dimensional. I mean, now the most prominent example is take the irreducible even-dimensional representation of SL2R. It is symplectic, and in fact in this case leads what is called to the Hitchin component of sp2 and R. But there are more components, maximal components than that. Okay, so so these are could say, well, you know, what are you going to get out more than whatever you have in Teichmueller space by doing this kind of construction? Well, it's by the fact that now the connected component of the representation variety of all homomorphisms into this here, containing this, is formed of maximal representations, and so you can construct. But deformate, that means take that guy, any deformation thereof is maximal. And most of them have the risky dense image, so okay. So that's the basic examples.
But over there they had discrete image.
Sorry?
Discrete image.
So that was one of the 150 characterizations, yes.
You lose that when you move to this setting.
Well, so that's my next thing. So I'm going to say two or three properties of maximal representations. No, I don't lose it. In fact, it's even better. Well, okay, it can't be better than SL2. It can be more interesting, though. Okay, so what higher Teichmueller theory now is trying, or what people in higher Teichmueller theory are trying to do is, you have basic hyperbolic geometry in dimension 2, which can express itself in terms of holonomy representation. You have, you know, some fundamental structures on Teichmueller space, and you ask, well, whether all this business, or to which extent all this business generalizes to these situations here. Okay, so whereas in SL2R, if you stick to PSL2R, you're faced with one component and its topology is understood. here you're going to have several components of which one will be contractible and others may have topology, etc. So, so there are new phenomena also, and in fact they are probably the most interesting part of this story. Okay. So what are some features of maximal representations? Here is a technical feature, which is how so maximal representations have, for example, the following property: they are reductive. That's kind of important for later. Then they give rise to quasi-isometric embeddings of the fundamental group of sigma with its word metric into sp2nr. So that answers, I guess, your question, because it's better than discrete and injective if it's a quasi-isometric embedding for any left invariant metric you want to put on sp2nr. That's better than discrete image, right? So they fall into this this class of groups about which are they called? Anosov groups, Leib-Karpowicz company. Okay. So this is one interesting property, I guess, and then, but that, if you want, that just comes from the fact that they are part of a much larger context and framework of what are called the Anosov representations, which sort of are one big generalization of that. Then there are more specific geometric representation properties which are satisfied by these guys and not by all Anosov representations. And in fact, that you have a specific color lemma. And maybe later on I have the language to say what it means exactly. Okay, so now what I want to talk about is the following. So one of the fundamental things, or maybe we leave this, in hyperbolic geometry is, of course, the Thurston compactification of Teichmueller space. So here is one instance. Via length functions on the fundamental group. Well, and the various interpretations of the boundary points. So these are length functions in the boundary, as in terms of, let's not be specific, in terms of either lamination, measured laminations or R3 actions with small stabilizers. And that's something you can aim to generalize to this context here. And it's a very natural question, because we do have length functions, which I will introduce now. Yeah, and the question is, to which extent does this Thurston picture generalize to this case here? So, okay, so now we can come to some specific definitions. So first, let's say what is the symplectic groups, probably good to remind. So length on sp2nr. So being in sp2nr means the following. So it means the transposed G times this matrix we're going to call J. G is equal to J. Okay. So that means that G is conjugate to its transpose inverse, or in other words, that the characteristic polynomial is palindromic. So that means that the eigenvalue structure of such a matrix is as follows. So the eigenvalues, I can list them here, list them with multiplicity. And if lambda is an eigenvalue, then its inverse must be. And I've ordered them such that the first n come in decreasing, well, of course the others also. The first n's are the ones of absolute value bigger or equal to 1. So most of the time these are complex numbers, right? So this is the absolute value of a complex number. Now the length of G and that's where we're going to depart with cat zero geometry. The length of G is going to be the sum of the logarithms of the absolute values of the eigenvalues bigger than 1. Okay? So if you have a real number which is bigger or equal to 1, its logarithm is bigger or equal to 0. So this is a sum of positive things. It's also the logarithm of the absolute value of a certain determinant somewhere. Okay? That's clearly. Okay. So this is the length function which is adapted to this kind of compactification. It's of course comparable to the, if you want the Riemannian translation length, then you would have to take the square root of the sum of these squares here. Okay, so you get length functions which are comparable but not the same. Okay, you can link it to the, this is of course linked to a Finsler metric on the symmetric space, which comes from an L1 type of metric. So somehow this is important also later on. Anyway, so now I'm going to recall, let's say, some special cases of theorem of and Parot from her thesis adapted to this situation here. So if we have now a homomorphism into sp2 and r, then let's say L rho, that will be the length function. Okay, so L rho of gamma is the length of rho of gamma. From now on, gamma will be the fundamental group of sigma, and G will be sp2 and r, which also suggests that what comes holds for more general gamma and G's. Okay, so in this way I get a map from maximal representations into length functions, and we're going to projectivize these length functions to sort of get exactly like in the Thurston setting. So we get a map which goes from this quotient to this thing here. As usual, this is with product topology, and that's a projectivized space. This is a space of reductive representations, and this quotient is nice. Just to give a little bit the idea that topologically this guy is homeomorphic to a real semi-algebraic set. So that's putting together a certain number of results in invariant theory. And this map here, so now a certain number of results from Parot are that the map theta, which, I should have said what the map is. The map theta, which to a representation rho associates the projectivized length function of this representation is continuous and proper. There are still compact fibers here. It's, of course, situation is not as nice as in the SL2 case, where it's rigorously injective. But it's proper, so there is sort of a relationship between this space and this image. The second thing is that the image of theta is open in its closure, which is compact. And that was sort of the point. So these are things which are not so hard to prove, actually. The compactness. And now I want to introduce a notation, namely for the objects we're interested in. It's, we're going to call L max sigma n. Well, this is going to be the image of theta, namely these are all the length functions of maximal representations, and the thing I'm then really interested in is the boundary of this thing. That's, in a sense, this is obtained in the following way. You know, any sequence of maximal representations, you look at the length functions and you try to rescale them so that they stay in a compact set, and you take a pointwise limit. And whatever you get there is in here, and then you ask questions about these length functions. Yes?
Is this injective on the maximal representations?
Is what? Injective?
Is theta injective on the maximal
No,
representations?
no. No, you know, once you have a centralizer, you may have representation of compact centralizer, and then you can take a homomorphism into this guy, and so the length function just doesn't see this. So here is an important point. I'm not claiming that this here will lead to a reasonable compactification of this space here. What I'm saying is that, what I have not said yet, what I might be saying next week in Oberwolf, that there are reasonable, I have something to leave something to say next week, right? I mean, there are too many conferences. That this guy here has natural compactifications in which it goes injectively, but that this length function thing here, this length function boundary, this length function compactification is an equivariant image of other reasonable compactifications, and worth to be studied, you know, by itself. But it's not going to sell us fantastic information about the topology of this quotient here, because you lose, you know, if you lose information like a whole compact fiber here and there, I mean, it's just, you know. So anyway. Okay. Next. Okay, so concerning this guy here, there are three theorems. The first one is a corollary of something we did 2 years ago with Beatrice, and only involves Beatrice and me. It's the very first question you ask. You know, the length functions of maximal representations, they vanish nowhere, because, you know, you have a QI embedding, so the length function itself as a length function is actually comparable to the word length, to the conjugacy word length. So a length function of a maximal representation is on the fundamental group is a proper function, right? So in particular, you're not going to have elements where it vanishes. So the very first question about the generacy here is to ask, well, could there be some, is the vanishing locus of the length function? Because that's what is going to tell you that things degenerate, right? And then you want to know how they degenerate. And here is the answer. So these are classes of length functions. So here's the geometric description, sort of. We're going to put the background hyperbolic metric on sigma. So put metric on sigma. So then we can talk about closed geodesics and surfaces with boundary, geodesic boundary, etc. So let L be one of these limiting length functions. So we're going to introduce a little definition. So a closed geodesic is going to be a closed geodesic C is L special if the following three conditions are satisfied. C is simple. Second, its length is 0, so the length of whatever representative of C is 0, but then what you want is that the length of any closed geodesic crossing it for any C prime which crosses it will have to be positive. So let's say here you have, for example, this is C prime and this is C. So somehow things got squashed here. Like in SL2, you just pinch a closed geodesic. That's typically you're going to have that. So, okay, so now, but clearly, you cannot have more than 3G minus 3 special geodesics, because with the definition I have given, that's they can't intersect, for example. So, so this gives you a priori a decomposition. This gives a decomposition of your surface into subsurfaces. With boundaries, the special geodesics. So then here's the first theorem. So you have these subsurfaces, and they're bounded by geodesics whose length is 0. So what happens for the rest? And so what happens for the rest is very simple. There is a dichotomy. So there is a dichotomy for every individual subsurface. Well, it can be either the length of every non-peripheral element is positive, so if you are on your surface and you look at the fundamental group of the subsurface, every element which is not peripheral has positive length. Of course, the peripheral elements are the special geodesics, so they have length 0. But everything inside has positive length. Or the length of everybody is 0. That should be, sorry, S index. So that then it you know that means that it cuts your surface into subsurfaces, and on some subsurfaces you have really a totally positive length function, and on others it vanishes identically. Now, so
In
yes.
the second case, you only have pair of times.
No, you can have. So take any geodesic, take any surface of genus 10,000, let's say, and the separating geodesic, and now pinch it, and so go to infinity. So what happens is typically the following: the length function of the left part is identically 0. The length function of the right part is identically 0. The length of the guy in the middle is identically 0, but the length of anybody who crosses this special geodesic is going to be positive. So, no, anything can happen. But the point here is the following. I said at the beginning of the talk that one can. I was restricting to surfaces without boundary, but the nice thing about maximal representations is that you can do this for surfaces with a boundary also. So in fact, what is going to happen here is the following. You see, here you're sort of happy. I mean, this will correspond to, I have not talked about it, this will correspond to a good action on a certain building where all translation lengths are non-zero. And that's a geometric situation. This here, you have the feeling you see absolutely nothing. But how could it happen that this length function on this fundamental group is 0? Well, you have a sequence of maximal representations. You have the length function, and you rescaled it. You rescaled it so that for the big surface it's okay. But for that small surface here, the rescaling was way too powerful and makes everything converge to 0. Well, nobody prevents you of rescaling this in a reasonable way. Now, just for the representation restricted to this subsurface, which happens to be maximal, and you get a new length function. And then, after, this is finite complexity, after finitely many iterations, you sort of have the asymptotic expansion of your length function in that sense. You can formalize this, of course, but that's why this fits very well. Once you set it up for surfaces with boundary, then you really have an iterative procedure to understand these length functions up to the last bit. Okay, now, so this tells us the following. So this tells us somehow that the next problem to understand is, what does it mean length functions which are everywhere positive? So that's the next thing. So theorem 1 tells us we're reduced to study length functions in the boundary which vanish nowhere. So here we're going to have to introduce the following, which is going to make the distinction between old phenomena and new phenomena. So what can typically happen is the following. If you are in the boundary of Teichmueller space, if you are in the Thurston boundary of Teichmueller space, you have a length function which vanishes nowhere, so you know it's associated to some measured lamination, right? And if you look at the minimal component of this measured lamination, then you know that there are small, you can find arcs, transversals of arbitrary small measure, right? So now you can close up, take such an arc which has very small measure, close it up, and you get a closed curve whose length is very small. In fact, you can construct iteratively a sequence of elements in the fundamental group whose length tends to 0. So, therefore, it is natural to introduce the following. We're going to look at the infimum of all the lengths of all elements which are different from the identity. We call this the systole of L, if you want. Okay, and so now, of course, systole of L is not well defined on projectivized length functions, but the whether it's 0 or not is a well defined property. So the second theorem says the following. I'm going to finish in time. Good. Sorry? Very funny. Okay. Okay. So this is this happened now here. Okay, it happened in Warwick, in Oxford here. So let L be a length function which we assume to be everywhere positive. For all gamma different. And we assume that, no, what am I saying? And nothing. So the following are equivalent. So remember, we're here in the representation is the sp2 and r. The systole of L is 0. And the second thing is, well, there is nothing new. There is a minimal surface filling measured lamination whose length function is L. So minimal means it's minimal lamination. Surface filling means that the complements are just ideal polygons with finitely many sides. And the length function of a measured lamination is what it is. I mean, you could say equivalently, L is the length function of a R3 action with small stabilizers. By Skorra's theorem, that's exactly the same. So that means that even though we are in higher rank, we're in sp2 and r whatever, if you have this here, if 0 is an accumulation point of the length spectrum, that's another way to say it, then you have not seen anything new. You come, okay, no. See, here there is a subtle issue. Then your length function comes from an R3 action with small stabilizer. Okay? The issue of, okay, there are other issues. But for the sake of finishing.
You said it comes from an R3?
Sorry?
So this function comes from an R3, from an action of the surface on an R3?
Yes, because. Now you see, I mean, now once you know that it comes from a measured lamination, then you know that it comes from an R3, right? Now this direction is not the difficult one. I mean, if you have a measured lamination on the surface, then you have an R3 action by Morgan and company. Skorra's theorem is the converse, that if you have an R3 action with small stabilizer, then you come from a measured lamination. But I'm not invoking these theorems here, I'm just giving context. You prefer that they replace 2 with 2 prime?
No,
L is the length function. It's
I don't see any R3.
You don't see the R3.
It's a lamination.
Okay. So add 2 prime. L is the length function of an R3 action So I know what you mean by I don't see an R tree, okay? And it's a very good question, which I hope to be able to answer. Where is the R tree is probably the most difficult of the questions here. Okay, so 6 minutes, so 7 minutes. So the question is example. So actually you can okay, so maybe what I should say that of course, you know, for SL2 that's the end of the story. So I have described for you everything which can happen for the length function in the Thurston boundary, right? The new phenomena come with SP4 already, okay? So that there are length functions which do not vanish anywhere and where 0 is not an accumulation point of the length spectrum. And it's not difficult to construct in SP4. I mean, if you take two length functions which correspond to measured laminations which are transverse, then L1 plus L2, you can make it a length function for a representation into SP4. Okay, I'm not being precise, but that's easy because you can make it into a representation into SL2 cross SL2, which you can send in SP4. And then you can apply some standard tricks to make it more interesting and bend it and make it the risky dense. But you have to prove that, okay, you have to prove all kinds of things. But so here you can construct examples. So that the set which I'm going to define now is not empty. Okay. Yeah. Okay. So maybe we don't need this. So let's call S. That's the set of all length functions well, whose systole is 0. So, namely, either that L vanishes somewhere and then it's taken care of by theorem 1, or it doesn't vanish anywhere, but the infimum, but 0 is an accumulation point of the length spectrum, and it's taken care of theorem 2. Okay, I have 5 minutes. So theorem 3 is the following. So let omega be the complement. Which is not empty starting with SP4. So let's say, yeah, number 1. So the most natural question is, well, okay, so this set is open at sort of non-trivial, because this condition of being systole 0 is not a closed condition in the space of length functions, of course. So this is open, and the mapping class group acts properly discontinuously on it. And that means that once you're away, that means that in this general length function compactification, there are two kinds of phenomena. Either the mapping class group has complicated orbits and then it comes from SL2, okay? Or you are in the region of discontinuity for it. And in fact, it's actually, it relies on the following property of length functions, namely that for every length function which appears in this thing here, there exist constants C1 and C2, such that so C1 times the conjugacy length of gamma is smaller or equal to L of gamma is more equal to C2 times the conjugacy length of gamma. That's about, so that means that out there are a lot of representations. Okay, this is more or less the best you can expect from a length function. Okay? So and I have 3 minutes for concluding remarks, or okay. So that somehow is the classical picture of all this stuff. What is really interesting is that behind that there are behind these length functions that there are of course actions on all kinds of spaces, and that was already, that was part of Anne's thesis, was to say, in a much more general context of a finitely generated group, a reductive group G, to say length functions obtained by compactifying in this way, they come from actions on certain specific buildings, and these buildings can be geometrically obtained as asymptotic cones of the symmetric space. Now, even better, in fact, what really happens is that to every such length function, one can associate a ultrametric ordered field. Ultrametric means, so ordered means ordered. It's even real close, so it's like the real numbers, except it has a norm which is ultrametric, which means that, and that's probably the most important thing, is that the norm of x plus y is more equal to the maximum of the norm of x and the norm of y. And the representation from pi 1 into SP 2 and f, so that now, well, the length function of that guy is the length function you're interested in. Because you see, you have eigenvalues, you have norm, you have logarithm of that thing, so you have the length function directly. The thing is, what this does here is that it puts you at infinity. Why? Because this tells you, for example, that the number 2 has norm 1 and the number 3 also. So all real numbers have norm 1. And this representation here is going to have matrix coefficients which do not have norm 1. So they are, so that tells you that these matrix coefficients are either infinite or infinitely small elements in that field, and this is what places you at infinity. Okay? And that's why, well, a way to study all that stuff here is to study representations into real closed fields, where you can then use all kinds of things which have been developed in real algebraic geometry. So, thank you for your attention.
Thank you very much. Are there questions?
You said that these particular length functions come from actions on buildings. Is that right?
Yes.
Are the orbit maps QI embeddings in that case? Does that come from 2 or not?
Here, orbit maps QI embeddings. I don't know yet. I mean, the action on the building is properly discontinuous. It has, and you know, there's this lower bound on the length function, so it's so that you can, there's a well-defined cat0 quotient, which has a lower bound on the injectivity radius, if you want. I think it's very, very plausible that these are QI embeddings. This thing here looks like one would have to deal first with the QI embedding question, but no. This is done via. This is done because we can associate to all these length functions. We can realize them as length functions of specific geodesic currents, and then work with the geodesic currents. But all this stuff is a little too fresh because it's from last week. So I don't know. You're probably right. I mean, there is it very much looks like you do have a lot of representations in a context, in a building context. In a building context where nothing is locally finite, and that's why it is possible. Because you know that the whole Anosov representation theory does not exist over periodic fields, right? We know that since. Because it would imply that you have continuous boundary maps, you know, that you can continuously send a circle into the Furstenberg boundary over something over QP. These are remarks made 2 years ago in MSRI. So it's a consequence of Kapovich, Leib, and company's work, right? But here, actually, and we work a lot with boundary maps about which we refrain from asking any kind of continuity property because that's not the point. But there is something Anosov going on, yes.
So if you're working with maximal representations and not is it possible to say yes why this won't work over SLMR?
No, this whole stuff should work for Hitchin representations. Yes. It just I don't feel like I mean we don't okay. Leave something for others too. Now, well, the geometry at some point, let's say these things here depend on much more on properties of geodesic currents. There is something which is considerably more difficult, is that here, fine, you have an R3 action, but you have, anyway, you know that you have also an action on a building, okay? So you have got to be able to relate these two things. So relating these two things, that is something which is difficult and might create other problems in the Hitching case, because you use a lot the geometry of the Siegel upper half spaces somehow. Specific features of it, I mean.
What about over SLNC?
So if you once you replace R by C, things get, as you know, terrible, because already with SL2C, then this is in the context of Anosov representation SL2C, but not anymore. You see something like when I wrote down, you have a color lemma. So a color lemma for maximal representations, now that we have length functions, means exactly the following: is that if you have a closed loop with small length, then any loop crossing it will have big length, and you can quantify this. And this is not true anymore for these representations into SL2C. But people studied this. Well, okay. I have no idea. I mean, with SLNC, it's already hard enough on SL2C. Yeah?
Is there some action on an R to the n tree lurking, where R to the n is thought of as an order of the beta and group?
R to the n? Which n tree?
Well, so an R, the way one normally think, an R to the n tree, right, is normally you think of it as kind of an R tree, and then you can blow up points at much smaller scales, and then like iteratively. And since you seem to have an R tree somewhere, and then you seem to have a variety of different scales, it seems a bit reminiscent of R to the n trees. The first thing here, we should try to put it into the context of lambda building, because that's what it would be. Right, so if you did that, then would you then get a lambda tree from your wherever these
probably get the lambda tree. We haven't worked out this. I mean,
whatever.
That's certainly a direction in which things are definitely possible. Because you have finitely many scales, but so somehow we concentrated on other things. But this one is definitely worth looking at. Mm-hmm.
Okay, so if there are no more questions, let's